Okay, so it's time. Let's start. So my name is Sapanjana and I am a PhD student in IIT Bombay. So I am also a TA in the NPTEL course MA85, and today session 5 week 5 discussion session. So today we shall solve some interesting problem, and in fact it is going to be a session where I will solve mostly all the problem in my choice, because last year assignment 5 and this semester assignment 5 almost same except 3 problems. So yeah, so I hope it is going to be interesting one. So let's share my screen. Yeah, so okay, so before going to this problem, let us go to the problem. Okay, this problem. So look at the question. What does it says? Yeah, so one thing to tell you again. Last year assignment 5 and this semester assignment in NPTEL course almost same. So today I have choiced in my own way some like in my career the problems that I found to be most interesting. Those are the problems I will try to solve. Yeah, so I hope you also will get it very interesting. Yeah, so let's see. So what does it mean for a sequence to not be convergent? So normally we know what is the definition of convergence. That if so let me first write the convergence definition, and then we will try to write the negation of that statement. Okay, so suppose L be a real number such that an converges to L as n tends to infinity. Now what do you mean by this? So you mean that for every positive number given, for every epsilon positive number given to you, given there exists at least one. In fact, if you get one, then you get all bigger natural numbers. There exists n naught belongs to n. So let me write here rather n naught on n naught epsilon, n naught epsilon, because the natural number that exists that obviously depend upon the epsilon, such that yeah, so what is that n naught epsilon, such that you know a n minus l that is less than epsilon, and this is true when that for all n greater or equals to n naught epsilon. But note that once you get such a number n naught which depends upon epsilon, so any number if you take smaller than this, then also it will take the condition will be true. I mean, if you choose n naught epsilon minus 1, that is obviously smaller than n naught epsilon, and then okay, sorry, if you choose any number bigger than n naught epsilon, I mean this condition is also true for all n greater or equals to, this is also true for all n greater or equals to k, where k is any natural number bigger than n naught epsilon. So when I write that here, that given positive number epsilon, you can find a natural number n naught epsilon that depends upon epsilon, you not only get 1, you actually get infinitely. And what are those? Those are nothing but all the natural numbers bigger than that. Okay, so this is the definition of the convergence of a sequence. Now let's try to see what is the negation of this statement. So suppose I want to say that the sequence does not converges to L, then what it would be? So now suppose an does not converges to L as n tends to infinity. So does anybody wants to try, or otherwise I shall proceed? Anybody if wants to try, please, because see, I am not able who is there or not, because my browser is closed. I am only looking at the this page that you are looking, so I will not have it. Anyway, so let's do. So that means this says that whatever positive number you give, I get a natural number. So this has to be false if I want to say n does not converges to L. So that means here it was that for every positive, so it says that for every epsilon given, so that means it has to be false. That means what? That you will get at least one epsilon, such that blah 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 blah, all these things will not happen. So let's write that much first. So there exists at least one, there exists one number, say epsilon number. So this says this is true for every epsilon. This has to be false, means you will get at least one, such that all these things will not happen. That means there exists one epsilon such that. Now let's come to the second part. It says that you find at least one natural number such that this thing holds. So this has to be false. That means you will not able to find any natural number such that this condition holds. So I am repeating again, if this has to be failed, then you will not able to find any natural number such that these things hold. The second here mod n minus these things holds. That means whatever natural number you take, this has to be false, such that for every or whatever natural number n belongs to, you take, this quantity has to fail. So let me write, for every to this one fails. Okay, so now let's try to write down what does it mean one fails. So let me write from here, that is there exists one epsilon greater than 0 such that for any n belongs to n. So this has to false, and what is the condition? That difference between an and L is smaller than epsilon for all n greater or equals to n not epsilon. So this should not happen for n. That means you should get at least one number bigger than this such that this false. So that means for every n belongs to n, there exists, so this has to was true for all n greater or equals to n epsilon. So there exists one, at least one k bigger than n such that this fails, such that this condition fails down. So that means if that is not true, then what is the negation? That is greater or equals to epsilon, but what is n, that has to be replaced by k. So you got the point. So now if I read the complete line, so there exists one epsilon positive real number such that whatever natural number you choose, that is for every n belongs to n, you will able to find at least one natural number bigger than that you had chosen, such that ak minus l is greater or equals to epsilon, right? Yeah, so this is the complete sentence. So let me write again. So there exists one epsilon such that for every n belongs to n, there exists k. So let me write this k to be depends upon n. So let me write it as kn, because it depends upon the natural number. So you will just immediately see an application of this problem. So kn, there exists kn belongs to n, and kn is bigger than n, and mod of akn minus distance between akn minus l is actually greater than or equals to epsilon. So I request you to try the same problem in general matrix space. There everything has to be changed in terms of the given matrix, not modulus. So you can try the same in general matrix space also. Yeah, just a minute. Okay, so no problem. So now so far so good. So now let's come to the problem that part B. We shall use this thing what we have just learned, that what does it mean for a sequence not to converge. So the question says that if I have a bounded sequence of real numbers such that every convergent subsequence of the given sequence converges to the same limit, so then I have to prove the original sequence an actually converges. So there are certain things to notice here, that first of all the sequence is bounded, one thing. Second says that every convergent subsequence an, it does not say every subsequence, it says only the convergent subsequences converges to the same limit, not to the different limit. So as per example, so now come to the problem 2. So as for example, if you take an equals to say 1 if n even and -1 if n odd, then you see it has only two convergent subsequence. One is for even, the other one is -1, although the sequence itself does not converges to any real number. So now here see, if I remove the condition that they converges to the same limit, then the hypothesis of this is failed, and hence you cannot conclude the n convergent. So the three things here very crucial. One is the sequence is bounded. Second is that every convergent subsequence, I am not saying whether all the subsequences. So you can take 3n type sequence, a3, a6, a9, a12, in that way. You can take a2, a4, a6, even ones, odds, or any subsequence. I am not taking on all subsequence. it's saying on all convergent subsequence of the given that converges to L, then this original sequence converges. Okay, so now let's start. So now I shall assume to prove we shall go by contradiction way. That means we shall first assume let's it does not happen, and we shall try to come out with a abstract statement. Yeah, so let's start. Suppose an does not converges to L. So now suppose an does not converges. That means there does not exist any real number such that it converges. Okay, so here it does not converges to L. Now what I have just said, so let us copy this line here, that there exists at least one epsilon such that for every n there exists kn depending upon n such that blah 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 holds. Now okay, so let me write again. So there exists, therefore there exists epsilon, positive number, say there exists epsilon such that for all n belongs to n there exists kn belongs to n and kn is greater than n, and mod of a kn minus l, that is greater than or equals to epsilon, right? Sorry, epsilon naught, right? Okay, so can I request one of you to be a co-host so that you can control who is joining or not? Please confirm if some wants. It is disturbing a lot. Yeah, so now if you choose vary all possible natural numbers, so for n equals to 1 there exists k1 that is greater than 1 such that I am applying this statement to 1. So and there exists k1 such that a k1 minus l, that is greater or equals to epsilon, right? Now if you take for n equals to k1, that is also a natural number, so then there exists k of k1 I should write, but to avoid the indices, so let me write k2 greater than k1 such that mod of a k2 minus l is greater than or equals to epsilon naught, right? Now for n equals to k2, again there exists k3 greater than or equals to k2, let me greater than, because this k2 such that mod of a k3 minus l is greater than or equals to, and you keep on doing the same thing. Okay, so in particular, see, now this has becomes a subsequences. So k1 and k2 is bigger than this, k3 is bigger than k2, k2 is bigger than k1. Thus I am writing in one line, there exists subsequence kn 1 to infinity of n such that mod of a k I minus l is greater than or equals to epsilon, and this is true for all I greater or equals to 1, right? So now here is the point comes that the given sequence, one of the hypotheses was it was a bounded, right? So now you have learned, right? So in one of the assignment, in fact in the last discussion session we have done it. Okay, let me just, this is page 5, add some pages here. Lots of hectic in online teaching, do this, do that, lots of stuff. Does it has gone. Oh, I should have after aged. Okay, so there exists a subsequence such that these things hold. Now an is a bounded. Now I had told this fact in the last discussion session. In fact, you have used in one of your assignment, as far as I know, that a is bounded. That is a very crucial part. Bounded. This implies that a k I, this subsequence is also bounded, right? 1 to infinity is also bounded, because there is the numbers coming from the original set. Now, by Boolean-Oerster's theorem, Oerster's theorem, there exist further subsequences. So let me to avoid notation, how do I write? So there exist subsequence. I have to somehow avoid conflict of notation. There exists subsequence a, say write k r. Okay, where, okay, so let me write nr, then it will be okay, where nr and r equals to 1 to infinity. There exists subsequence a k n r of this sequence a k I, such that there is a subsequence and a real number and a real number and some L naught belongs to R, such that a k n r converges to L naught as n r tends to infinity. Now come to the second hypothesis, that whatever subsequence you convergent subsequence you take, again be careful that it is not saying about all subsequence, it is saying only about convergent subsequence. So whatever convergent subsequence you take, it says it converges to the point L. So that means the L naught has to be L, no other choices. It is by hypothesis. By hypothesis, L naught equals to L, right? But you so you have got one thing, that difference between okay, so let me mark it as star. You have arrived to the contradiction, but just need to mention. Okay, so from star a k n r minus L, that difference greater or equals to epsilon, and that is true for all n greater or equals to 1. Okay, so I have just, this is true for the sequence, and a k n r is a further subsequence of this a k I sequence. So if I put those numbers, that also valid. So now come to this the convergence, and so this says the a k n r converges to the L naught equals to L, but this condition says that this does not converge. So you are getting two conditions at a time, so which is a contradiction. So in this problem, what I have done nothing but the use the negation of the convergence of the sequences. So that's why I had first done that problem, which is contradiction, and hence a n converges to L, right? And as n tends to infinity. So if you have any doubts, then you can just ask. Otherwise I shall move to the there are other part in this problem, so to that part. Yeah, so just wait a minute. Okay, so now the part says let an be a sequence of real numbers such that every convergence subsequence of n converges to the same limit, then the sequence n converges to L or not. So see, these two statements exactly same, but the hypothesis that boundedness has been removed. So that's why this can't be a true. In particular, if you look at the sequence, so part C, take xn equals to n. So it does not have any convergence subsequence, and in fact the xn also does not converge. It satisfies hypothesis, but xn does not converges. Xn. So boundedness is very crucial. Does not, or you may think that it does not have any convergence subsequence. You can take this one to be n if n by 2 if n even, and minus 1 by n, let 1 by n odd. So now if you look at the subsequence 1 by n, then it converges to 0. It has one convergence subsequence, but the even subsequence, that is increasing rapidly, so the original sequence can converges. So x2n minus 1 converges to 0, but x2n diverges to infinity. Let me not use the convergence symbol, use diverges. Okay, diverges to infinity. So if you have any doubts, then ask, otherwise I shall move to the next problem. Okay, so no problem. Look, come to the problem 1. So now come to the problem 1. Which of the following is true? Now you can do it very quickly. So every sequence of a real number has a convergence subsequence. You just have seen that my n sequence, it does not have any convergence subsequence. So that Boolean-Weierstrass theorem, why boundedness is so much important in that theorem. Basically this problem is on the hypothesis, this problem is only for the importance of boundedness in Boolean-Weierstrass theorem. Whenever I write BWT, that means Boolean whenever I write BWT, that is Boolean-Weierstrass theorem. So the first one, that you have one counter example, so this is not going to be true. Every sequence of real number has a monotone subsequence. Okay, so let me go to, so it is going to be true, but why? Let me just quickly recall. Every bounded sequence of real number is convergent. Obviously that is not true. Minus 1 whole power n, such that n belongs to n. It is a bounded and oscillatory sequences, so it does not converge. So you have learned, I hope, the concept of peak, if I am not wrong. Have you learned that? Please confirm one of them, otherwise I shall quickly tell and skip the problem, because once I looking at the lecture videos, then I found that sir taught the concept of peak. Okay, so let me just quickly say and then skip. I shall skip this problem. There is no point of doing the same thing again and again. So peak, say suppose xn is a sequence, then any member, say xn naught, is said to be a peak if xn is less than xn naught for all n greater or equals to n naught, right? That means the n naught is an upper bound of the set xn such that n greater or equals to n naught, as simple as that. So that is xn naught is an upper bound of xn such that n greater or equals to n, right? So now in order to obtain the monotone subsequence, construct a monotone subsequence from a given sequence, you consider three cases. Case 1, when xn does not have any peak. Case 2, when xn has finitely many peak. Case 3, when xn has infinitely many peak. You just use the definition. I have forgot what is the lecture videos number, but you can find it, sir has done. So anyway, so and it is one of the part in the proof of Weierstrass theorem that whatever bounded sequence you take, you found a bounded a monotone subsequence by that construction, and by monotone theorem that a bounded monotone sequence converges to the supremum. Yeah, so on that you conclude the Weierstrass theorem. That is the basically proof, and it is the first step of Weierstrass theorem. Okay, so I hope these problems no doubt for you. For B, let me write here B. Okay, so let's come to this problem. Yeah, so this problem is one of my favorite problem. I hope you also will found this to be interesting one. Okay, so the problem says that, so let me just ask, so if you have any doubt, then please ask. So I think only one of you are there, so if you not following, then please ask.
Till now, don't doubt, sir.
Yeah, okay, so fine. So I hope this problem will be interesting for you. So the problem says that an defined by 2, in that way sum up to 1/2 1 by n, that is a conversion. So if I am not wrong, then this problem has been done in Friday's discussion session, but still I have choiced this problem because I have some different approach for this particular problem. So let me show you. And the technique that I am going to show you, so it will help you a lot, not only for this particular problem. So you can apply in many series where all the terms are positive. Okay, so first let me draw a picture. Just wait few minutes, let me draw a picture here. Okay, so now this part, let me use different color. Okay, so here all the lines, although does not looks straight perpendicular to the horizontal one, but all the things will be very perpendicular. I mean, it will be very straight. Yeah, so I am not good at drawing at all. Anyway, so now let me here do something over here, add something over here. Okay, and here also the gap gradually gone 1, that is 2, that is 3, 4, 5, 6, and say this is n, this is n plus 1, and this is n minus 1, that is origin, and this is your x axis, this is y axis. And so now you have some I hope you have got that this is nothing but the curve 1 by x. It looks like in the positive part, if you plot, then graph looks like in this way, that it as much as it tends to 0, it blows up, and if you take x tends to infinity, then it gradually tends to 0, right? And yeah, so now this is the graph, and here what I have added, that I have drawn a rectangle here. If you just look this rectangle total, and here, so what is the base? That is 1 to 2, and so length of the base is 1, and what is the height here? That is 1. So although it looks rubbish, because see here 1 is this much, but here 1 is so much, so I have drawn in that way only so that the picture gets bigger and it does not confuse you. Okay, so now here I have drawn a rectangle. So if you look at the rectangle, then what is the area of this rectangle? So this area of the rectangle is base into height. I think yellow will be problem to look to visibility. Oh, sorry. So base times height, that is the rectangle area. Rectangle area. And what is that? In that case, base is 1, because 1 and 2 difference is 1. And what is the height? This is the point for the graph. So if you put x equals to 1, then you get y equals to 1. That is the height of this is 1. So 1 is 1, right? Here x equals to 1 implies 1 equals to 1. So that is the area of this box, first one. So now if you look at the second one, so here also the base is 1, because here the base is 3 minus 2 is 1. And what is the height? This quantity, what is the this much? That is nothing but x equals to 2 on the graph, then you get y equals to half. Yeah, so this height is basically the half, and this is the, and the base of this rectangle, full one, this one, that is a rectangle whose base is half, and height is, base is 1 and height is half. So base times height, rectangle area, equals to 1, base and height is half. Now if you do the same thing here, then you get base into height equals to 1 into 1 by 3rd. So now if you look at this series, that the first term is 1, that is nothing but the area of this rectangle, half, that is nothing but the area of the second rectangle, 1 by 3rd, that is area of the third rectangle. And in general, if you look over here, then here, that is base again 1, base is always 1, base into height equals to 1 into height of this is 1 by n minus 1. And if you look at the next one, then you show this one, then you get base height equals to 1 into, now height is 1 by n, right? So basically the term an is nothing but the sum of areas of all those rectangles. So let me put the sum of all rectangles in the above picture. I hope this clears to you. So now one thing that to be noticed over here, that the rectangle always was had added some areas more under the graph. If you naturally look the area under the graph, that would conclude only this much only, here this much only. But in each of the cases you have added some extra amount of areas to each of these rectangles. Say for example, in this case here you have added this much, in this case you have added this much extra areas. Right, and in each of the cases these are the parts where you have added some extra areas, and always it will be able to get some extra because it tends to 0, it never gets 0. And which, so let me now write the line in one line, some of the which added some extra areas under some to the area under the graph of y equals to 1 by x in between 1 to n plus 1, right? Because I have right here 1 and the maximum is n plus 1. Okay, so let me write whether it is right in the above picture, which added some extra areas, which added some areas, extra areas to the area under the graph of y equals to 1 by x in between 1 to n plus 1. Okay, so now you have basic concept of integration in class 12, that you know how to integrate. Now if you look at the integration, now look at integration 1 to n plus 1 dx by x. What is this quantity? Later we will calculate, but geometrically what does it says? It says the area under the graph, and here the function is 1 by x that I have considered. So if you integrate 1 to n plus 1, basically it is saying the area, total area from here to here. I mean if I want to highlight this, let me try if there are other. Yeah, so basically the area will be total this much and all these things. That is the integration, that is the area of the, that is the area under the graph, right? So that is the integration, and you have added some extra amount to the number an. So now let's calculate. So that is actually log of n plus 1, right? and it is very clear from the picture. It is very clear from the picture that log of n plus 1, that is the area under the graph, is less than or equals to sum. In fact, that is strictly less than 1. It does not matter actually. Let me write equal sum of the areas of the rectangles drawn above. Okay, so that is basically nothing but the term a n plus 1. A n equals to 1 plus half plus 1 by 3 1 by n, and this is true for every n. Now if you are interested, you can check at home what would be the upper bound of this quantity a n. I mean, try at home, try to find the upper bound of a n in terms of log of some function of f n. I mean, you try to find the sum half plus, you do not start from 1, you start from half, 1/3, 1 by 4 up to n. At that time you just consider the area below the curve here, 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 and you see. I hope you will able to do it, but you have to give some time. That is the point. Anyway, so what I needed, that I have got. So log of n plus 1 is less than or equals to a n, and thus the series n equals to 1 to infinity 1 by n does not converge, because you know that log n plus 1 is an unbounded sequence, is an unbounded sequence. If that was convergent, then it converges to some finite number, and if you take the limit, then left hand side is blows up to infinity, whereas the right hand side would be finite, and so it does not converges. Now you can conclude all the things. So it cannot be a Cauchy sequence because R is a complete field. So if there is any Cauchy sequence, so it has to convergent, so it cannot be a Cauchy. Obviously that you have just seen that it does not converges. It is a divergent series, obviously, and obviously not oscillatory because it is strictly increasing. Okay, so let me just point out the points. So A not true because R is complete field. Here all Cauchy sequences converges, that you have seen. Convergent, not convergent by above argument. Third, C, divergent from above, and not oscillatory because an is strictly bigger than strictly bigger than an minus 1, that is strictly increasing function, because you are adding 1 by n type of terms to every time. So this is true for all n greater or equals to 2. Yeah, so that is the thing. I hope this was interesting for you. Okay, so you can apply the same idea not only for this particular problem. Here the function is 1 by x. Whenever you find series something like log x by x, or any series that has positive term and you know the graph, then you can actually have a look at the graph, and without any test of the series, you by picture you can conclude that whether the series convergent, divergent. Yeah, obviously in exam you have to write subjective exam, then you have to write everything in details, but this clears much more concept. That's why I have told you. Okay, so now problem 1, problem 2 is done. I hope this is there is no doubt in this. Okay, let me do this problem very quickly. This is a very easy problem. So I have to find the sum of the series. So let me first simplify this term, and once you simplify, then you will able to do it. So let an equals to 1 by 4n square minus 1 n greater or equals to 1. So now you can write the term as 2n minus 1 times 2n plus 1, right? Now I want to, so one of small guess from here is that all the terms here, the factor 2n minus 1, here the other factor 2n plus 1, they are coming consecutively. I mean here it 1, if you put n equals to 1, then it is 1 and then it is 3. If you put n equals to 2, then it comes with 3 and the second terms it comes 5. Now if you look at compare n equals to 1 and this term n equals to 2, they are same, so somehow they will cancel. That is the sense. So let me do the same thing that I was saying. Okay, so what extra I have added, 2n plus 1 minus 2n will cancel out, plus, so I have added 2. That is okay, right? Okay, so now if you look at the partial sum sequences, what is partial sum sequence? a1 plus a2 plus dot dot an. So let me take half to the common. So if you put an equals to 1, that I was just saying, so that will be 1 minus 3, right? The a2, now it will be 3 minus 1 by 5, and again sorry, that will be nil. So if you put 3, so the first term is 5, which is equals to the n equals to 2 case for 2n plus 1, and to keep on like this, and finally at the nth step you get 1 by 2n plus 1, right? So basically, so all the terms will in that way cancel out, and what will you remain, it will be 1 by 2n plus, and that is n greater equals to 1. Okay, so now what is the sum of the series? That is nothing but limit of the sequences. So summation n equals to 1 to infinity equals to limit of the partial sum sequence, right? And what is the partial sum sequence? I have arrived that 1 minus 1 by 2n plus 1, and if you take limit, the second term tends to 0 and the first one is half. So basically what you have found, that you have found the sum of the series is half, and if you in fact more clearly write, half equals to, if you put n is 1 by 4n square minus 1, so that is first term is 3, second term is, if you put n equals to 2, then what you get, 4, 16, 15. And if you put n equals to 3, then what you get, 8, 4, 32 minus 1, 31. Now if someone gives you a series in this form, then you have to first put in a general form in this way. here it has been already given in the form for n square minus 1, but if someone gives you 1 by 3 plus 1 by 15 plus 1 by 31, then you have to formulate the general form that a sequence which is giving 3 for n equals to 1, which is giving 15 for n equals to 2 and giving 31. So after that you can do that. Yeah, so in that case you have to first find the form of the sequence, but that is itself is a course that how to, because always it may not be easy to find such a form. So that is another course where you will learn how to generalize the terms of the sequences. You may not able always, but there are certain situation or cases where the generalization, I mean there are formulas and ways to put in a form. Yeah, it is not always possible to put every time in a particular form. So you know now this is wrong, this is wrong. Okay, so this problem is done. Let me check whether I have left any problem in above. 1, 2, this is done, this is done. Okay, so now this is one of my favorite problem and interesting one. I hope you enjoy this one also. So what does the problem says? That if I have three positive numbers, so alpha is bigger, beta is bigger, and gamma is also bigger number, all strictly positive numbers. Okay, and they satisfy alpha, beta plus gamma less than or equals to 1. So from here one thing that you can conclude that since all of them are positive, so alpha beta is also less than or equals to 1 and gamma is also, because alpha beta is less than or equals to sum and gamma is also. But one thing to be pointed out that gamma never cannot be 1, because if gamma is 1, then alpha beta is alpha beta is 0, but that means one of them has to 0, which is not possible. So basically from here what you are getting, that is gamma is actually strictly less than 1. Okay, because of this condition. So now come to this problem that I am constructing a sequence Pn by setting P1 equals to alpha, which is positive. Now I shall inductively, I think you have seen this type of sequences.
Sir, I have a doubt.
Yes, sure.
Sir, what if alpha beta equal to 1? Then gamma would become 0, right?
Okay, so that also, yeah, very good point to notice here. Yeah, I did not notice is because I did not require this. Yeah, okay. Yeah, that is also strictly less than 1. Yeah. Okay, so I hope you have seen this type of sequences where the nth term is being constructed by using previous ones, as for example n minus 1 or n minus 2. There are lots of possibilities there, and I don't know whether sir has told you or taught you that about the Banach contraction theorem, that if you can put sequences in this way, f of Pn, where f is some function, then there are some theories. I hope this is not covered yet, because you peoples are not yet aware of continuity and differentiability. So anyway, don't confuse you, forget things whatever, when time will come you will learn. So inductively the second term what would be, the from the formula, that will be Pt equals to P1 by beta P1 plus gamma. So one thing that is clear from here, that this is also strictly positive number, because if beta P2 is 0, then P1 would have been 0, but that is not the case. So that you know at least. So in that way I shall use induction to show that every Pn is actually strictly positive number. So now my claim is Pn is strictly positive. So you assume that Pn minus 1 is positive because you have got the result 1 and 2. So assume Pn minus 1 is strictly positive, and if you want to show that Pn is positive, that is the next term. And you want to show the next term is positive. So that means you want to show this is positive. Without loss of generality, you assume that this is 0 by contradictory way. So if that is 0, what is the formula of Pn? If you put here n minus 1, then you get Pn minus 1 by beta Pn minus plus gamma, that is 0. This implies P of n minus 1 is 0, but you have assumed that is positive, so that is a contradiction actually. That if you assume n minus 1 term positive, then the nth term is positive. And not I have told you here mathematically, but you can actually see from here that Pn plus 1 equals to beta Pn plus gamma. So from here you can actually directly conclude that Pn is 0 if and only if Pn minus 1 is 0, because if you Pn 0, then here Pn minus 1 has to be 0, no other choices, right? So anyway, so that is been proved, no problem, which is contradiction. So my first claim that Pn is true, that has been established, right? So now I will show that Pn is actually a bounded, right? That will be very easy. That claim, that will not be that much difficult from its definition. Beta Pn plus gamma n greater or equal, is bounded. So since you have found now beta Pn is, I have seen positive, so this quantity beta Pn in the denominator, beta Pn plus gamma, that is also positive. Therefore, okay, let me write in blue. Therefore beta Pn plus gamma is also strictly positive, because all the numbers are positive for all n greater or equal, and all of them are strictly positive. Okay, so there is no confusion here. And now beta of Pn, that is strictly less than beta Pn plus gamma. So if you take the ratio, then you get 1 by beta Pn, right? Now if you just, since Pn is positive, so inequality will not be changed if you just multiply it by a positive number, and this is possible only because Pn is positive, otherwise inequality would have changed. Okay, so now and what is the term in the left hand side? That is basically Pn plus 1, and here Pn cancel out because it is positive, and you get that is beta, and this is true for all n. So basically what you have got, that Pn plus 1 is less than 1 by beta, and if you combine the first one with this, then you get 0 less than Pn less than 1 by beta for all n greater or equals to 1. So basically what you have got, that Pn is a bounded sequences. Okay, so now one of the common theorem in showing a sequence convergence is that show bounded and monotone, right? So now my next job is to show whether it is uh, uh, monotone or not. From Boolean-Weierstrass theorem, now one thing is guaranteed, that you have at least one subsequence that is convergent. Now question is whether the original sequence converges or not. So claim Pn. I request to follow this very carefully, because the technique will be used here will be very helpful if you carry on with mathematics, and I don't know if you just yeah. So now sorry, this is monotone. Okay, so let's calculate Pn plus 1 minus Pn, that is difference between two consecutive terms. Just put the formulas that is from given, that is beta Pn plus gamma, and that is Pn minus 1 by beta Pn minus plus gamma. So let's compute, simplify this term. So in the denominator what it will be? It will be beta Pn plus gamma times beta Pn minus plus 1 gamma, right? And here it will be multiplied Pn times beta Pn minus 1 plus gamma minus Pn minus beta Pn plus gamma. Okay, so now let's look closely. So here beta Pn minus 1, and here also one term present, that beta Pn minus 1, and with negative sign, so they will be cancelled out. What will survive? That is Pn times gamma minus En minus times gamma, and denominator beta Pn plus gamma, beta Pn minus 1 plus gamma. Okay, so in write the numerator in this way, Pn minus 1, and denominator is beta Pn plus gamma, Pn minus 1 beta plus gamma. Okay, and this is true for all n greater or equals to 2, because here I have written n minus 1. Yeah, so it seems like it has gone here. It is in the subscript. Okay, so now if you want to show monotone, either it will be Pn plus 1 greater than Pn, or Pn plus 1 is less than 1. You can say equality also, whatever, but these are the only two possibilities. That means this total term here, it has to be either positive or negative. Okay, so but one thing, that the denominator term beta Pn plus gamma, that I have already proved that it is a strictly positive number, that just here. Okay, so if this term is either positive or negative, that only depends upon the positivity or the negativity of the term involved here. Because gamma is positive, it will not affect in any way. So I mean, if I write, note that thus Pn plus 1 minus Pn is greater than 0 or less than 0 if and only if Pn minus is greater than 0 or less than 0. Okay, if that is positive, then this term is positive, then this is positive. If this is less negative, then that is negative. Now if you do the same thing for this term, what you get, that Pn minus 1 minus that is greater than 0 or less than 0, the same calculation will follow here, and keep on doing this, and finally where you will get, the first term is bigger, that is n plus 1, So you will achieve that is or less than 0. So basically what you are getting, Pn plus 1 minus Pn is positive or negative if and only the term P2 minus P1 is positive or negative, right? Okay, so I hope this is clear. And what is this term? Alpha by alpha, because P1 was defined to be your alpha, and alpha, beta plus gamma, that was less than or equals to 1. If you take ratio, that will be greater or equals to 1. So basically alpha, because that is given, right? And what is alpha? That is P1. So one condition that you already know, that P2 is actually, that is P2 greater or equals to P1, and hence Pn plus 1 minus Pn is greater or equals to 0, that is greater or equals to Pn, and that is true for all n greater or equals to 1. So what you have got, that Pn is actually increasing sequence. Thus is bounded, because you have seen that Pn less than 1 by beta and monotone increasing. Monotone increasing. Therefore, Pn is convergent. Now, if you want to solve more problem like this, then you can look at this book. You will get at least 1000 many problems. If you want to try this type of problem where the sequence has been constructed by using its previous term, the one of the favorite sequence and well-known sequence that you also might know, that is Fibonacci sequences. Example, an equals to an minus 1 plus an minus 2. Here the sequence is constructed by adding its previous two terms. For more problems like this, you can follow Kagzor-Noack part 1. It has 3 parts. Kagzor-Noack problems in real analysis. In my career, whatever I have learned in analysis, I have thoroughly followed these 3 parts. Kagzor-Noack 1, which is for sequence and series and all the real number system inequalities. The second one is on continuity, differentiability, integration, and the last one is measure theory and general integration and Lebesgue integration. So if you can do these 3 books, no one can stop you in analysis. Anyway, part 1. Okay, so no problem. There you will see lots of problem, like the whole book is only on series and sequences. So I hope this, but there are, I think, one part more. So now we have concluded that whether the sequence converges. Now the question is, if so, find the limit of the sequence En. Okay, so now let us assume that limit to be L. So let us calculate what is the limit. Finding limit. Okay, so you have seen that Pn converges, so we can now assume let Pn converges to some number, say L, and L belongs to R. In fact, it will lie between 0 and beta. Let me put 1 by beta, because Pn was in this interval, it will be equals to. Okay, so one thing that I want to say, whenever you get a sequence which is bounded and it is monotone, if it is monotone, then it converges to its supremum, because if you look at the set Pn, and then that is also a set, it has bounded set, it has supremum, so the sequence Pn will converge to the supremum, and if it is decreasing, then it converges to the infimum. That is for general information. So basically here L is nothing but supremum of the set, supremum of Pn such that n greater or equals to 1, and if it was decreasing, then it would be infimum. Anyway, so now look at the formula of the nth term, that is beta Pn plus gamma. So if that is the case, if you take the limit on both sides, because this is a sequence of real numbers, that is also sequence of real numbers, and you have seen the properties of convergent sequence, that sum of two convergent sequence converges, ratio of two convergent series where the ratio is not 0, then converges to A by B form. You have seen all these things. So by taking limit n Pn plus 1 equals to limit of n Pn by beta Pn plus gamma, and what is this? That is L, and here it is L by beta PL gamma, because if Pn converges, then beta Pn converges to beta times L, and beta Pn plus gamma converges to beta L plus gamma, and L cancels out, and what remains, that is beta L plus gamma is equals to 1, that is L equals to 1 minus gamma by beta, and that is the limit actually. Okay, this is the limit. And one thing that I want to also mention, whenever you find a sequence in this form, at the very beginning, how will you guess whether it will converge or diverge? For that, you directly assume that it converges, and in that case the limit would satisfy this equation, right? Here in general, if you take a sequence in this form, for example, let me write general. So suppose Pn plus 1 equals to f of Pn, right, for some function. Here the function is 1 by here f of x equals to x by beta x plus gamma, right? If you put x Pn, then you get the, but in general, then you try to solve this one, f of L, where f is a continuous function. You don't know f continuous at this moment, but later you will see. I am just introducing the terms so that in future you don't get scared of. Okay, so from there you notice whether you are able to solve or not. Notice whether solvable or not. Then you can predict whether the sequence converges, because if it is not solvable, then how can you find the limit? It cannot converges. So if it is not possible to solve, then you can directly conclude that it does not converge. As for example, in competitive exam, you can directly use this type of concepts. These are the short tricks to check quickly. But if somehow the solution possible, then you have to prove that it is monotone, bounded, etc. to show that the sequence is convergent.
So first we have to check the continuity and then check whether it is solvable, right?
No, that is not where I have read continuity is that Pn convergent, but how can you push the limit to the inside? I mean, if you take the limit here both side, say, then what will you get? That is equals to limit n f of Pn. but here what I have written here, for that I need to push this limit inside. I mean that is limit NPL. That is the thing I have used here. But why that is possible? That is true for a continuous function. That is why you need continue to. At this moment you may not know these things, but don't worry, you will learn in this course also only continuous functions.
Okay, sir. Thank you.
Yeah, this is just for your advanced information I was saying, because see, sometimes when the contents gets over, and if there are something that needs to inform the learners, then if the time goes past, then you may miss it. That's why I have mentioned, because when you will learn the continuity, then you will learn very carefully, because you know you have some uses of these terms in these concepts. That's why I always introduce all the things related to those things which will be required, so that in future you know what is the importance of learning these things. Otherwise it will be like blah blah blah, the abstract things are going on, why should I do this? Yeah, so here is the one short trick that you try to solve. Here the function is continuous, so when you learn continuity, then after at the end of this course, then whenever you find problem in this format, at the very first you try to solve this type of equation by taking limit, and notice whether it is solvable or not. If it is not, then it cannot converge, because it was a convergent, then you would able to find the limit, but you are not able to find, so it cannot converge. Yeah, so that is one nice thing to be taken from here. Yeah, so anyway, so you will learn continuity. For the timing, skip this problem. So you have got the limit also, that it is actually 1 minus gamma by beta. Okay, so let me show you one of my other best problem. Just a minute. This problem has been discussed. Yeah. Now one of my best problem. Let me. This problem is very easy. If I get time, then I will do it. But for the time, where is the problem? Yeah, these two problem. This is one of my favorite problem. So I hope you get this to be interesting. These are the problems which I had been asked in during my admission in PhD, and in fact in MSc times also. So yeah, anyway, so what does the question says, that I need to show or conclude whether a sequence is convergent if certain things happen. So what is given, that the convergence of every subsequence an. Suppose I have a sequence, yes, so let me first clear the question. What is the question? So I have a question. I have a sequence an, right? Now the question says, if any subsequence of this sequence of the form a n s, where s is positive, so that means if you take a real number, say s is bigger than 1, then look at the subsequence a n s, n equals to 1 to infinity. Now how does this this subsequence look like? For example, s equals to, you have taken 2, then it looks like a2, then the second term will be a4, then a6, a8. If you take this is for s equals to 2, if equals to s equals to 5, then you get a5, 10, a 15, a 20, in this way, and this is true for every. Here see, so the question says n is a sequence such that all subsequences in this form ans convergent. Now can you conclude whether the original sequence is convergent? So problem seems like very interesting, right? So like you can think that I can cover all the subsequences, all the terms, but yeah, so what do you think? Because the solution, if I take tell you the solution, then it will be just like, yeah, so it seems like, but intuitively what do you feel? Like someone ask you randomly, then what is your first guess could be? Okay, so let me show you. So question you have got that whatever subsequence in the form ns, where s is in your hand, you take, multiply and take the subsequence that converges, it is given, but question is whether the original sequence converge or not. So the answer is no, actually, because one of the point to be noted from here, the subsequence when you are considering n dot s and s is given to be greater than 1, because if you put s equals to 1, then you get the original sequence, because then it is nothing but an, that is not given. So s greater or equals to 2. So basically all the terms a, I mean n dot s, that is a composite number. Note that n dot s is a composite number, not a prime. Composite number for all s greater or equals to 2, that is greater than 1. So basically what this problem now reduces to, that an is a kn converges for every subsequence where n runs over composite number, but it does not says anything about the primes. So if you define some different value at the primes, then you cannot cover that subsequence by this way, because primes don't have any factor. Only possibility there would be s equals to 1, but all the other terms can be covered by multiplying some number, because they are composite numbers. Only terms that you cannot cover by multiplying s is the primes, because in that case you have to take s to be 1, and s is you cannot take s equals to 1 because that is not given to you. Okay, so that is the main trick here, and you can never cover the primes by multiplying s by s greater or equals to 2. So consider since this is false, you have to provide a counter example. So this is the counter example. You can play with your friends that if a sequence satisfies these properties, can you conclude the sequence converge or diverge? Consider an equals to, say, 1 if p is prime, and 0 if n is not prime. See, so then ans n equals to 1 to infinity and s is greater or equals to 2. ns is a composite number, that is not a prime number, that is actually the zero sequences. So that is convergent for every s, converges to 0 for all s greater or equals to 2. But if you look at the subsequence pn, and there is a point, you know that there are infinite many primes. If the number of prime would finite, then you would not able to construct such a subsequence, because for that you need infinitely many terms. Okay, so here that is the very application of infinite number of primes. Yeah, application of existence of infinite number of primes. Okay, so the an sequence does not converges because the subsequence apn an here does not converge to L belongs to R, as apn, where pn denotes the nth prime, converges to 1, not equals to 0, en the nth prime. Okay, yeah, so that is the conclusion. Yeah, I think this problem was interesting for you. The next one, that is also a very interesting one.
Sir, I have a question here.
Yeah, sure.
Sir, if we assume that all these subsequences we take by ANS converges to the same limit, then will the sequence be convergent?
Then also I think may not possible, because if you remember the first problem that we solved today, that was saying that if I take all the convergent subsequences converges to the same limit, but then uh, uh, so what is your question? Can you say me, because I am getting confused? Yeah, please repeat.
Actually, in the question, if we read this, let us say convergence of every subsequence of AN after form, ANS is greater than 1 to the same limit inside the convergence of the sequence A.
Okay, so yeah, now I have got. Now you are not considering all possible subsequences, only considering the subsequences of this form, particular form.
Yes, yes.
Yeah, so because see, there are some other problems. I think it will not be true. My intuition says, but let me check at home, because I don't want to waste time, your time. Yeah, so I will obviously
Okay, okay,
discuss in the next discussion. Yeah, sure.
okay.
I shall discuss uh, this problem, and you try. You also try at home. If you get that is good. Otherwise, I shall discuss.
Okay, sir.
Yeah, I shall discuss this problem in next week. The question is, what happens if all subsequences of the form ANS n equals to 1 converge to same limit. Yeah, very good point actually. Yeah, thank you. I shall obviously look, at least for me. You also look at home. Yeah, so now let's solve this problem. This one also very interesting. So the problem says that if I have a sequence whose subsequence is a2k, a2k plus 1 and a3k are convergent. I am not saying anything about the limit. I am only saying their convergence, because there is a theorem that if you know that even sequences and odd sequences converges to the same limit, then the original sequence converges. But here that is not given to us. That's why one extra condition that is given, that A3k, the sequence that is multiple of 3, that is convergent. Now my target is to show that AN is convergent, right? So first what, so we know if A2n and this sequence and A2n1 sequences converges to L, both converges to both. Just if both of A and both converges to L, then AN actually converges to L. That we know, right? There is no confusion on this. Now here the given hypothesis that is not given. So my target is somehow show that A2k and A2k plus 1 both converges to the same limit by using the extra hypothesis that is given to us, A3k, right? Okay. So my target is to show limit k A2k equals to, I can take limit because I have given that they are convergent. So that is they are same by using a 3k that sequence converges. Okay, so my target is this one. If I can show, then we are done. So let assume, take the limit, let limit k A to k to be L and limit k A to k plus 1 to be M, right? So now my, and also there is one more, A3k, A3k equals to say L M N. Okay, so now my target is to show L equals to M. So now look at the subsequences. Look at A6n. So this is a subsequence of both of the sequences A2k and 3k, because 6n, the set, that is a subset of 2n such that n greater or equals to 1, and also subset of 3n. Not only 3, you can take any scalar multiple of the LCM of 2 and 3. So this problem has general version that you can replace by 2 and 3 and by any number. So that is good. Anyway, so if you look at this, that is a subsequence of both of A2n and A3n, and if a sequence converges, you know that all its subsequences converges to the same limit. So now A2n converges to L, A3k converges to N, and it is a subsequence of both these. Therefore what you get, that L equals to N, because this is a subsequence that will converges to L, and by uniqueness of limit they are same. By uniqueness, that is a sequence can converge to at most one point. Uniqueness of limit of sequence. Okay, so you have got L equals to N. Now if somehow you can show that N equals to M, then your job are done, because then L equals to M equals to N, all are same. So now again trick here, these problems are like observation, how carefully you look at the problems. Look at A 6n plus 3, I think, if you lower. Okay, so this is all the numbers 6n plus 3, if you take common n, then that is obviously a subsequence of so that is subsequence of 3n such that n greater or equals to 1, and 6n plus 1 3 equals to 3 2n plus 1. This quantity is odd, this is odd. If you multiply two odd numbers, then it is still always odd, so it never gets even. So in particular, the subsequence 3n plus 3, that is also a subset of this set, that is all the numbers are odd. Basically what I have got, that a6n plus 3, that is a subsequence of the sequence a2k plus 1 and a3k, which is these are the questions that you may be asked during the interviews or competitive exams, which is a subsequence of a 3k and a2k plus 1. And now you know that this converges to m, so its subsequence converges to m, and this converges to n, so it converges to n, and this implies m equals to n, and you have already proved that this is actually equals to L. So your job is done. So all the limits actually same. So now you can try at home by replacing here 2 and 3 by some other numbers. And not only this, see all these numbers 2k, 2k plus 1 and 3k, they are partition. I mean you can write disjoint union of infinite sets, the natural number set, and in that way you take, say for example, 5 disjoint set whose union is n, and obviously all of them are infinite, otherwise you cannot consider sequences. So as for example, you take 5 disjoint infinite set whose union is n, and you assume the convergence of the respective sequences and try to show the convergence of the original sequences. Okay, yeah, so you can try the general problem, but let me just add a page 60, 14, 15, 16. Okay, so there are second part of this problem, that does the convergence of any two of these subsequences imply the convergence of the sequence. That means if you just assume either a2k plus 1, or you assume a2k a3k, or you assume a2k plus 1 a3k, then can you conclude? So obviously your guess is now no, because you have no control over the limit, they may be different. If they were same, then there were a chance. So second part, this will not be very difficult. I am writing just 3 examples. You take you can check this home. These are very easy. That this is the for a2k converges to 1, a2k minus converges to 1, but the original sequence does not converge. So the first one part, an does not converges to L, L belongs to R, it does not converges to any L. And the second one, if you take 1, if n equals to 2 power n, 0 otherwise, if it is not of the form 2 power n. See, if you want to, sorry, excuse me, I can't hear you.
Nothing, sir. Just finishing.
Is it okay everything, or if there is anything?
Yes, sir.
Yeah, okay. So if you want to construct a counter example that a3k converges, a2k plus 1 converges but the original one does not converge, then what will be your target? That if you look at the subsequence a3k format, that is multiple of 3 and all the odd ones. So common ideas will be, look at the all other numbers which are not covered by these two sequences, that is odd and multiple of 3. What are the all possible such numbers? So think about the numbers which are not odd and multiple of 3. So one of the choice is that 2 power n, it neither odd and neither it is a multiple of 3. So these are the numbers that cannot be covered by the sequences a3k and a2k plus 1. That's why I have taken such a infinite subset of the natural number, say 2 power n. You can choose any other one which does not intersect the set 3k, such that k belongs to n, and the odds which does not hit the set. You take an infinite set and define a different number and 0 otherwise. So then you see, you got the point how I have constructed these sequences. Then a3n that converges to 0, a2k plus 1 converges to 0, but an does not converges to any number. Now you got the point how I have constructed. See, once you know the counter example, that is fine, but you should also learn how to construct counter example, and that will clear your concept. Constructing counter example is the part where the concepts gets clear, and you will clearly see the picture, visualize the problem. So construction is much more interesting because you have to find a subsequence which is not covered by 3k and odds. And if you, for the third one, if you just look at the numbers, that an equals to say 1 even and minus 1 odd, then I think you got okay, which one I need actually now? This is 3k 2k, this is 2k 2k, and I think I need now 2k and 3k, right? Okay. Okay, so 2k and 6k, you can define 2k if n even and 0 otherwise, or what else, if n even, so you should get a number which is not covered up by multiple of 2n and 3n. So basically events. Okay, so define one if n is prime, 0 otherwise. So this cannot be covered by 2k 3k, the set of all primes, and again I have used the power of the existence of infinite many primes. So then a2k converges to 0 because all the terms are zeros by definition, and a3k that is also 0 converges to 0, but the original sequences does not converge. L belongs to R. Okay, so these are the three counter examples. So again, the constructing the counter example is the most important part, that actually clear the concepts, and the conclusion is that you cannot assume the convergence of the any two to conclude the convergence of this set. Okay, so I think I have 10 minutes left, so I had few problems but let me show the interesting one, this one. So let me solve this one because I have only 10 minutes. So I think I will able to prove in between this 10 minutes. Okay, so rest of the problems we can discuss in the next week, no issue. So I had done one problems like this. I have forgot, but I can recall that this type of problem I had done. So if alpha belongs to q, then alpha is of the form p by q. So now you have to show that limit of this term. So basically first you have to find n factorial alpha pi. So if you n factorial alpha pi, that is 3 up to n, and this is p by q pi. So this implies n factorial alpha pi is a natural number if, so if you want to cancel out the term q, then you have to take n large, so that 1 to n contains q. So basically if you take q at most, so that is the term q is present there, then this will cancel out and total term will be a natural number, right? And once that should not include pi. Yeah, so that belongs to if n greater or equals to q, and you already know now that convergence of a sequences is not affected if you just rearrange or the finite many terms, or you change the values for the finite many terms, then its convergence is not affected, and which follows obviously it's from its definition, right? So now sin n factorial alpha pi is equals to 0, because that is a natural number, n times k pi, that is 0, and this is true for all n greater or equals to 0, and this implies limit n sin n factorial alpha pi is 0. So first part is done. That was actually easy. Now the part that says that sin n does not exist, that also I was asked in interview. So now to show limit n sin n does not exist, right? So now assume by contrary assume limit n sin n equals to L for some L belongs to R. Okay, so now look at the now I will use the identity that sin square theta plus cos square theta equals to 1, and for that I need to conclude whether the sequence cos n convergent or not. So for that, look at this thing, cos of sin of n plus 2 minus sin n. You can take here not only 2, you can just n plus 1 or any number, you can do the same thing. So not only nothing special about 2, nothing special about 2. Take any real number, obviously take positive, otherwise you may have some considerations. Anyway, so now what is the formula? That sin c minus sin d, that is actually sin cos of c plus d by 2, that is n plus 1 n 2n plus 2 by 2, that is n plus 1, and sin of c minus d by 2, that is sin 1. That is the thing you have learned in class 12. So from here, and if you take limit left hand side, that is 0, because if sin n converges to 0, sin n plus 2 is nothing but the subsequence of that. So they converges to the same limit, and this one here will be limit n sin 1, but you know sin is 0 if and only if it is a multiple of pi. So from here you conclude that if sin converges, then cos of n plus 1 actually converges to 0, right? Now you also look cos of n plus 2 minus cos of n. Do the same thing, because you know the convergence of this, that is equals to sin of c plus d by 2 sin n plus 1 sin d minus c, that is sin 1, but minus 2, sign of minus will come with a negative. Okay, and this one converges, so the total thing that will also converges, so that is limit n to sin, I have just adjusted the negative, sin 1. This implies, again if you just cancel out all the term, that you get sin of n plus 1 is 0. So you have got two things, cos n plus 1 converges to 0, sin n plus 1 to converges to 0, but you know that cos square n plus 1 plus sin square n plus 1 is equals to 1, and this is true for all n greater or equals to 1. But if you take the limit, then limit, by taking limit you get left hand side 1, but the right hand side, this quantity should be 0, because you know the both of them converges to 0, so their square also converges to 0. By taking limit, you get 1 equals to 0, which is absurd. So sin n cannot converge. So you can try that same thing for taking any real number, do all the, just use the formulas. And the last part, that is over here, let me do this one, that is also exactly same, they are exactly same, but yeah, so since I should conclude all the related information, that's why I have put it. So here you know that if you take rational one, then this one converges to 0, you have just seen. But if you take the alpha to be irrational, then it does not converges, because intuitively what is the point here, after certain stage all the terms were multiple of pi, but since it is an irrational number, you cannot cover, I mean you can never make it an integer, because if at any time it becomes an integer natural number, then alpha has to be rational number, no other choices. So that is the thing that you assume by contrary that it converges. So let me add page, what is the page number there? You just 1-2 minutes more, because it is 59, it will not take that much time, just 1-2 minutes maximum. Okay, so limit n sin n does not exist. Okay, and for the second part, you again assume limit n sin n factorial alpha pi exists finitely, then consider sin of n plus a, where a is large enough. That will be a subsequence, like I mean you took a subsequence from these sequences, and proceed exactly in the same way that was proved for sin n, and proceed exactly in the same way as did for sin n. So it will not be that much difficult. You will able to do this because in fact if you want to say, then I can in fact say that sine of n plus 1 and the sine of n minus 1. You just look these two subsequences. Sorry, there will be alpha. Then also you can conclude. Just use that difference and sum formulas here, as like in this case you use the things, you will obviously get, and obviously we have to use somehow this thing. Okay, so I had some other problems, like this problem was very easy, but I wanted to discuss this problem. But anyway, what we shall discuss, I wanted this problem to be discussed because it was a very nice one. Anyway, so we shall discuss in the next week. So if you have any doubts, then you can ask. Otherwise, I have just one thing to ask from you. So if you have any doubts, then you ask. Otherwise, after that I shall ask.
No, sir, I don't have any doubts.
Yeah, so one thing that I wanted to ask you, like, is the contents that I am covering is helping you or not? Like, because you are giving time here, it is my duty. See, I am as a PMRF student, I am PMRF scholar, so my duty is to come live to help you students who are learning over through NPTEL. So my point is, why will you waste your time? Because it is my duty. If you don't come, like in the last semester when I was teaching integral and vector calculus, then no one would come. I would teach to myself. Like I am teaching to myself, no one would come, and yeah, so at that time it was okay that whatever I do, it will not bother. But since you are giving 2 hours, so you should be benefited from here somehow, because I am doing my duty. So if you have are not getting benefit, then please tell, like, how should we proceed, or the level of the problems difficulty, like you are not able to face, or it is too easy, like any type of things, or any particular problem if you want to discuss, that also you can say that you are trying at home. Yeah, that is the thing, like what is the thing, if you are getting benefited, that feels very good, that I am able to teach someone. But yeah, so it is my duty, I am doing.
Sir, actually, it's really very helpful. Actually, when the first problem, which is and like that, and the n is greater than like that, and that problems is more useful to me. My concern is I'm preparing for GATE and NET exam. So if we teach the tricks that you taught today, that continuity thing like that,
Okay, okay.
it will be more beneficial for me.
Okay, so you are preparing for JE advance, right?
No, no,
Hmm.
GATE exam and the CSIR note.
Okay, gate.
I'm a BC graduate.
You are preparing for gate exam, right?
Yes, yes.
Okay, sure. I shall obviously try, because in net gate type of problems, there the trick parts, and because you need to do lots of problem in a short time. Yes, sure, I shall keep in mind. Yeah, so thing is, that's why I ask. Like, if you want anything to be discussed, then only we will able to know what to be need to be done. Yeah.
Yes, sir. I really want the problems to be solved in more precisely and in very short duration. That would be more helpful for me.
Okay. Yeah, so because see, I normally what I do, I want to tell all the things around that problem. Suppose I am telling you one problem, then I try to cover all related problems to that problem. That's why I tell things. Yes, sure, I shall try my best to find problems related to the exam that you have just said. That
Yes, sir. Also, I wanted in your approach, the covering all the aspects of the problem, that will be more helpful. And apart from studying for GATE, I also like learning all the aspects of the problem. I like discussing maths deeply, particularly analysis. That's why I joined the
excuse
NPTEL.
me, I think your voice was cutting, so can you please repeat? Your voice was cutting, like dropping too much. That's I can't hear properly. Hello, hello. Yeah, okay. So I don't know. Maybe there are some internet issues. Uh, I am not able actually hear you, so that's why.
Yes, sir. I can't hear from you clearly because there is some internet issue from my side.
Yeah, yeah, it is obvious because it is 2 hour session, so it is very difficult because I am using institute internet. That's why there is no issue from my side, but I understand. Yeah, so we can talk in the next, but for next week I shall try to formulate more problems like this, so that you get most of it benefited. Okay, so thank you, bye, see you in the next week.